Okay, can everyone see the screen well enough? Okay, brilliant. Well, thanks again for the invitation. It's a great opportunity for me to talk to material scientists and people working in metamaterials, because I'm personally very interested in understanding more about this field, because I think there's a huge potential for what I'm doing to use metamaterials. So, like I said before, I'm a roboticist. I work in the field of soft robotics, and I see my role here today a little bit as somebody coming from the outside, and my role is to throw you some curveballs and make some suggestions and get the discussion started. But in order to do so, I think I have to tell a little bit about what I'm coming from, so you understand what I try to do. But it will not be about robotics, what we're talking today, but really about metamaterials. And the connection that I've been signed up for was with artificial intelligence and active mechanical metamaterials. And I think one of the main themes that I would like to propose here for discussion is that I think the connection between artificial intelligence and the physical world, which is currently not there, can potentially go through intelligent materials, because a lot of successful things in artificial intelligence / machine learning has been done in the virtual realm, where you have like millions of billions of pictures or simulations of board games, or you play computer games. These are all very abstract kind of concepts, but when it comes to the real world, there's a large bottleneck through the embodiment of any kind of physical interaction. And I think the metamaterials can help there actually to solve this problem. So I see metamaterials as one way to solve or provide the bridge from artificial intelligence to reality. Now, I'm saying that because I work in the field of robotics, and robots is exactly that. So where you have this kind of abstract intelligence on one side and machine learning side, but a robot by definition has to interact with the environment. And I'm very interested in understanding how we can build better bodies for our robots. And this is a concept that is usually referred to in our field as morphological computation, which proposes that the body morphology, and this is not just the form and shape, but also dynamical properties, ways to change the bodies and so on, can actually implement useful functionality for any kind of intelligent machine. And this is very bio-inspired. And usually I share a couple of videos to show what I mean by that. So this is a very famous video of a trout in a lab tank. It's a so-called Kalman Street vortex, where you have this kind of flow coming from the left to the side. And you see the fish is doing exactly what it's supposed to do. It explores a little bit, moves around. But there's something really, really interesting going on with respect to the morphology of the fish. And I give you a couple of seconds. Maybe you can see it. If not, I'll give you a little hint. This is actually a dead fish. So what you can see here is a fish that is attached to a nylon string and is still able to exploit basically the forces of the environment and have this very beautiful natural swimming movement. Now, from a roboticist's perspective, this is really interesting because it's extremely energy efficient, very interesting what the body can do. But obviously, it's very closely connected to the material properties. Let me give you another example. This is the so-called rhodium seed, which has this very peculiar kind of spiral in the back. And when this seed falls to the ground, a lot of things are happening until the conditions are right, which means when it starts to rain. So when there's a little droplet put on it, it suddenly unravels it and it drills the seed right into the ground. So in the material, there's this energy stored, there's a detection, change of humidity, basically stored, as well the actuation there as well. And when you talk to biologists, this kind of principles that there's functionality in the morphology and in the material properties, this is kind of common, it's ubiquitous at any domain, at any scale. This is a solution that evolution has found and has been using it long before there were any brain cells or any kind of neurocircuitry available for machines, biological machines. So maybe another example in the sensing side, so the insect eye has this little small kind of smaller eyes, which are very primitive. Now, very interesting for flying insects, they have to deal with a nonlinear effect, which is called motion parallax, which means basically if you have an object that is in front of you, and even if the relative speed to you is exactly the same, it changes depending on the perspective, and it swooshes back to the back, and then it goes slower again. It's like when you sit in a train and you observe like a church tower. It's very, very slow, and then it passes very fast. So there's this kind of nonlinear relationship between the angle of the object relative to your flying kind of trajectory. Now, interestingly, if you look very closely, there's a nonlinear distribution of this ice. So they're more dense on the side than on the front. So in the picture, you can't really see it very well. But what this kind of morphology is doing is it's linearizing this nonlinear kind of input data stream and helps the brain, therefore, to do something more simpler. So even just very simple morphological structures can help to simplify the problem for whatever comes after that. If it's a brain or some neurons in a biological system, or a machine learning algorithm in, for example, a robot, or in an intelligent building, or a clever morphology like an exoskeleton, or whatever you want to look at. So what I think is that morphological is basically this kind of physical interface between the physical environment and the abstract kind of digital world of machine learning. So the body sits in between, and therefore it has to do something in between. You can design the body in such a way that it's basically out of the way, and that's the way we usually build robots. We make them as simple and stupid as possible, like having stiff robot arms, so you can model them very easily, but the body doesn't do anything, basically, besides it looks similar than a human, if you have a humanoid robot, for example, but beyond that, there's no intelligence there. But if you have intelligent materials, you can do things. And there are two sides of the coin here. So on one side, the body can help to improve the interaction. So it could be like the fish example, that it actually interacts with the environment, right, for locomotion. But for artificial intelligence, it could be also, it helps to sense the environment. So very complex environments, it can help you to extract information more reliably, or more consistently, or more specifically. And the other side of the coin is also the body can help to facilitate the learning side. So it can speed up learning, and I'll talk about some examples later on. I put and control in the bracket because there will be another session, but of course it can help to simplify the whole control problem as well, but also learning to control, for example. Now, let me give you 3 categories with some ideas that we could have as a starting points for discussion. So one is if you have this kind of sensing, right? So it could be that the morphological layer that you build up with metamaterials serve as this kind of first layer in a more complex structure. Like if you look at deep learning, there's a first layer, second, and so on, many layers. That's why it's called deep learning. And every layer makes more and more abstract kind of feature extraction. And if you design the body cleverly, it can do that for yourself as well, being directly or being at the interface of the real physical world. It actually can interact with the physical world. So you can get something like feature extraction. So if you look at convolutional neural networks, they're inspired by the way our visual kind of information is processed in the brain. There's this kind of neurons, visual neurons, they're closely connected, they're localized, connected, and we can do something similar with forces, for example, or they're local in frequency, so they vibrate at similarly frequency responses, and therefore you can extract some kind of features, and therefore you do some pre-processing of the data, like the insect eye, for example, but also in a more dynamic way, for example, not just statically linearizing the data. You can have dimensionality retraction. Maybe you have a lot of data, and then it can help you to actually reduce it to a few very important features or dimensions that are more relevant by going through a clever morphology with metamaterials. And of course, we've shown it, for example, in some theoretical work and with robots as well. It can serve as a machine learning kernel, which basically translates a low-dimensional input signal into a high-dimensional space, but does it in a nonlinear way. And suddenly, things that you want to separate, and you couldn't separate originally, get separable with hyperplanes. So you can use simple linear regression because the body is doing this kind of separations. It could be in the time domain, in the frequency domain, whatever you need, for example. And also noise reduction is something that is very important for working in open world scenarios and real world applications, which you usually don't have with abstract data, where you have to artificially add the noise, right? But the bodies, especially mechanical bodies, are really good at damping out things, right? They are low pass filters, but you can design it also differently, emphasizing specific kind of frequencies. and it helps you to reduce the noise. And also redundancy, because if we have clever manufacturing techniques, we can make a large number of the sensors in the millions, and if 1 or 2 breaks, or 10 or 1,000, it's not really relevant. But if you have one sensor at the joint and it breaks, the complete system breaks down, for example. So we can have this redundancy, and we get closer to what biological systems are doing, where they have like millions of sensors, very cheap ones, really bad ones, but the average is a really, really good estimate and very useful information. And let me talk about a certain class. This gets more to the adaptive side. So if there's a way that we can adapt the body by changing morphological features, so this could be very specific ones, or certain subregions, certain degrees of freedom, certain dynamical properties, and metamaterials are perfect for that. We suddenly can do many more things than with just a very static body. So we can have adaptive sensing. It has been shown, for example, that if you, in palpation, for example, if you want to find metals in the body for cancer detection, for example, it's very important that you're dynamically interacting, that's one part, but also that you change the stiffness in your probing. So changing it helps you to extract more information. Also, you can have mode switching. Maybe you have 2, 3 different modes that are pre-programmed in the material, and it uses the same learning algorithm, but then you make a switch, maybe some buckling, maybe some snapping, and then suddenly it transduces basically information in a different way, and you make it easy for you to learn. Also, if you have different modes, it's easy to learn, right? Because you don't have to learn everything at once, but you can learn the smaller subsets, so you can accelerate the whole learning approach as well. And you can have memory effects, right? You can remember things. You can remember how many times you've bumped into something and change the materials in an adaptive way. You can change the sensitivity of different body parts. You can imagine the skin on, let's say, a robot fish, right? There are certain parts that move more, and this kind of stimulation will change the morphology over time, which change then the sensitivity there, depending on what you need. You can make it more sensitive or less sensitive, for example. And another thing is to outsource knowledge. So this is, if we learn a new task as humans, for example, we are very brain driven. We look at somebody showing what we have to do, for example, a new, like a tennis swing, and then we're very much in the brain, but over time we goes to the more subconscious level, and we could even go to the morphological level. We could outsource learned functionality into the body, and then the brain is freed up for doing more interesting stuff. Or the machine learning approach. And if there's something that is new, it goes back into the brain side of it and then readapts the body, for example. And then finally, this goes more into the machine, using machine learning for using machines. That could be a robot, but it could be intelligent furniture, intelligent clothes, it could be intelligent buildings, it could be anything that it has a physical interaction or a need for a physical interaction with some kind of intelligence. So you have this kind of full feedback loop there between the body and the environment and the brain, for example. And of course, usually when I have these complex systems, it's really hard to learn to use them. And one way that the morphology can help is to constrain the space. So this goes back to the example that I mentioned. If you learn a new kind of skill, we also stiffen up, reducing basically the dimensionality, because it's less dynamic, and then we're getting really good, we're getting more and more dynamic. So you could actually mechanically constrain the search space for your learning algorithm and then open it up more and more. Similar, you can do that with growing. Now growing, I mean growing in a very, very general sense. It doesn't mean that you have to literally grow volumes or material, but in very substantial change of morphologies. So you can like have some swarm-like adaptation, you can increase the body by doing something. And again, it's the same. If you learn with the body with 1 degree of freedom, it's easy to find a solution. And if you change slightly the body, you find that the new kind of solution is very close to the previous one. So you look in the space here, and then you make the more complex the morphology more and more. And basically, you lead the optimization process along with you. We've shown some simulation where we grew a tadpole into a frog, and it accelerates actually the growing quite significantly. It makes it more robust. And then finally, exploiting dynamics, right? Can we build a body with materials that have a potential for many different solutions? And then we basically just learn for this specific environment, for this specific task, how to exploit the given body. So the design is then not about a specific solution, but more like a solution space that we could investigate. Now, these are just some of the ideas that would go into this direction. They're very general. They don't have to be robotic at all. That's just my starting point. And these are just the ones that I throw here into the discussion. Obviously, we don't have to discuss any of those. I'm happy to discuss any kind of things as well, obviously. Thank you very much.